In April 2025, an astronomer at MIT pointed the James Webb Space Telescope at a faint reddish smudge of light that almost nobody had paid attention to before, a candidate object buried inside years of archived data, one of hundreds of similar smudges that needed careful follow-up before anyone could say what they actually were. It looked, at first glance, like nothing special, just another point of infrared light among thousands cataloged in a routine deep sky survey. What came back from that observation turned out to be light that had been traveling toward Earth for so long. It left its source when the universe was only 280 million years old, roughly 2% of its current age. It is, as of right now, the most distant galaxy ever confirmed by humanity, and the details buried inside its light are forcing astronomers to reconsider some of their most basic assumptions about how the earliest structures in the universe were able to form at all. This is the story of MOEMZ14, and why a single point of light, fainter than almost anything else ever studied in detail, has become one of the most consequential objects in modern astrophysics. To understand why this discovery matters, you first need to understand how astronomers actually measure distance and time at these cosmic scales, because the two turn out to be the same thing. Light does not travel instantly. It moves at a fixed finite speed, roughly 186,000 miles every second, blisteringly fast by any human standard, but nowhere near fast enough to cross the truly vast distances involved in observing the universe's own past. When you look at the sun, you are seeing it as it existed about 8 minutes ago, the time its light took to cross the 93 million miles separating it from Earth. When you look at a star in the night sky, you might be seeing light that left its source hundreds or thousands of years earlier. When you look far enough away at an object billions of light years distant, you are looking directly into the deep past, watching light that departed its source before the Earth itself had even finished forming. The farther away an object is, the further back in time you are actually looking, which means the very earliest era of the universe can only ever be studied by finding the very faintest, very farthest, very oldest light still reaching us today. Astronomers measured just how far back using something called redshift, denoted with the letter Z. As the universe expands, the space between galaxies stretches, and the light traveling through that space gets stretched along with it, shifted toward longer, redder wavelengths. The same basic principle behind why an ambulance siren drops in pitch as it speeds away from you. The higher an object's redshift, the more its light has been stretched, and the further back in cosmic history you are actually observing. MOEMZ14 has a confirmed redshift of 44. To put that in perspective, that number corresponds to a galaxy whose light left its source roughly 280 million years after the Big Bang itself, an almost unimaginably early moment in the history of everything that exists. The universe today is approximately 8 billion years old. MOEMZ14's light is showing us what existed when the universe was barely 2% of its current age, a period astronomers call cosmic dawn, when the very first stars and galaxies were only just beginning to form out of a universe that had, until that point, been dark, cold, and filled with nothing but neutral hydrogen gas. Finding a galaxy this faint, this red, this far back in time is not something any previous telescope could have managed. The James Webb Space Telescope carries a primary mirror more than 21 feet across, the largest ever launched into space, built specifically to gather enough infrared light to detect objects whose visible light has been stretched entirely out of the range human eyes, or even Hubble's instruments, were ever built to see. By the time light from an object at redshift 14 finally reaches Webb's mirror, it has been stretched so dramatically by the universe's own expansion that essentially none of it remains in visible wavelengths at all. It arrives instead as faint infrared radiation, precisely the part of the spectrum Webb was engineered from the ground up to detect. Hubble, for all its own historic discoveries, was simply not built with the right combination of mirror size and infrared sensitivity to ever have found something like MOEMZ14 on its own. This particular frontier of astronomy, the search for the very first galaxies that ever formed, genuinely did not exist as an achievable target until an instrument like Webb was actually built and launched. The discovery did not happen overnight, and the story of how it was found says something important about how much of modern astronomy now depends on patiently sorting through enormous quantities of existing data. The team, led by astronomer Rohan Naidu, was specifically combing through archived images captured earlier by Webb, searching for objects that showed the particular telltale signature of an extremely high redshift, a very specific pattern in how an object's brightness changes across different wavelengths of infrared light. MOEMZ14 stood out as a promising candidate among many, one of hundreds of similar objects that needed dedicated follow-up observation before anyone could confirm what it actually was. In April 2025, the team turned Webb's instruments directly toward it, and by analyzing its full spectrum, the precise breakdown of exactly which wavelengths of light it was emitting, they were able to confirm its extreme redshift with a level of certainty that a simple brightness measurement alone could never provide. The result, once confirmed, immediately displaced the previous record holder, a galaxy called JWST Z14-0, which had itself only set the previous record less than a year earlier at a redshift of 32. That pattern, records being broken again within months of being set, is itself worth pausing on, because it tells you something about how quickly this particular frontier of astronomy is currently moving. JWST Z14-0 had already stunned astronomers when it was announced in 2024, discovered by researcher Kevin Hainline, who has described the moment he first saw the data as startling enough that he stood up from his desk. Researchers involved in that earlier discovery described the galaxy as unlike anything predicted by theoretical models and computer simulations built to describe what the very early universe should actually look like. It was surprisingly bright, roughly 5 times more luminous than any previously known galaxy at a comparable distance, a level of brightness that immediately raised uncomfortable questions about how a galaxy could have grown large enough and formed enough stars in the extremely limited amount of time available since the Big Bang to produce that much light. One of the astronomers involved in that discovery, George Rica of the University of Arizona, said plainly that nobody had dreamed there would be galaxies this bright at this high a redshift. MOMZ14 did not resolve that tension, it deepened it. Because MOMZ14 is not simply a slightly more distant cousin of JWST Z14-0, sitting quietly a little further back in cosmic time. It is bright too, bright enough that astronomers studying it have had to seriously grapple with exactly the same uncomfortable question that JWST Z14-0 first raised: how does a galaxy manage to become this large, this luminous, this quickly, when the universe had only just finished its first few hundred million years of existence? The standard model of galaxy formation, the framework nearly all modern cosmology is built on, describes a slow, patient process. Small clumps of matter, guided by the gravitational pull of dark matter, gradually merge together over hundreds of millions and eventually billions of years, slowly accumulating gas, slowly forming stars, slowly building up into the kind of large, luminous galaxies we see filling the sky around us today. That model depends heavily on dark matter behaving in specific, predictable ways, clumping into structures called halos that act as gravitational scaffolding, pulling ordinary matter in and giving newly forming galaxies something to assemble around. Under that model, a galaxy existing at 280 million years after the Big Bang should still be small, faint, and barely assembled, a loose scattering of newly forming stars, rather than anything bright enough to be detected clearly across the entire observable universe, simply because there has not yet been enough cosmic time for enough dark matter, halos of the right size, to have formed and merged together. MOMZ14 and its immediate predecessor do not fit that description. They are bright. They appear to already contain a substantial, actively forming population of stars. And they exist at a point in cosmic history when, according to the standard model, there simply should not have been enough time for that kind of structure to form. This is not a small discrepancy easily absorbed by minor adjustments to existing models. Some researchers working on this broader problem have pointed out that if galaxies this massive and this luminous really were common at these extreme redshifts, there may simply not have been enough dark matter halos of the right size and the right age available to host all of them, a genuine tension between what is being observed and what the underlying theoretical framework can currently accommodate. Researchers studying MOMZ14 have been careful and precise in how they describe this tension, and it is worth being precise here too, rather than overstating what has actually been established. This is not, at this point, a confirmed crisis that has broken cosmology, and responsible scientists studying these objects have been consistently careful not to claim that it is. What it represents is something more specific and, in some ways, more interesting. A genuine, growing gap between what theoretical models predict should exist this early in the universe's history and what Webb keeps actually finding when astronomers point it at exactly this kind of target. One line from the research team studying these extreme early galaxies put it directly, describing a growing chasm between theory and observation related to the early universe, one that raises compelling questions still very much waiting to be explored. There are a few genuine competing explanations currently being investigated for why galaxies like MOMZ14 appear so much brighter and more developed than models predicted, and it is worth walking through them honestly because none of them has yet been proven conclusively. One possibility is that star formation in the very earliest galaxies happened dramatically faster and more efficiently than current models assume, perhaps because the gas available at this early stage in cosmic history was purer, less polluted by the heavier elements that later generations of stars would produce, allowing stars to form in tighter, more efficient bursts than anything we observe happening in galaxies today. Another possibility is that these earliest galaxies contain unusually large numbers of extremely massive, extremely luminous stars, a stellar population, skewed toward giants in a way that would make a relatively small, young galaxy appear far brighter than its actual total mass would otherwise suggest. A third possibility, one that researchers involved in this specific line of study have flagged as particularly compelling, is that some portion of the light coming from these objects may not be starlight at all, but radiation generated by an actively growing supermassive black hole at the galaxy's center, material heating up and glowing brightly as it spirals inward, adding a source of luminosity that has nothing to do with how many stars have actually formed. That last possibility connects MOEMZ14 to a broader, stranger pattern that has emerged across many of Webb's other early universe discoveries, cosmic objects that appear far more massive, far more luminous, or far more developed than the standard timeline for galaxy and black hole growth would predict, showing up again and again in different surveys, at different redshifts, studied by different research teams using different methods. MOEMZ14 is, right now, the single most extreme example of that pattern that has been confirmed, sitting closer to the Big Bang than any other galaxy in the astronomical record. But it is not an isolated anomaly. It is the leading edge of a growing catalog of objects that all seem to be quietly asking the same uncomfortable question: whether our current understanding of exactly how quickly structure was able to form in the infant universe needs a meaningful revision. There's also something worth appreciating about just how rapidly this specific frontier keeps moving, because it says something about where this research is actually headed next. NASA itself has publicly stated that it fully expects Webb's newest record to be broken again, likely sooner rather than later, as astronomers continue combing through archived data and scheduling new, dedicated observations aimed specifically at finding galaxies from even earlier in cosmic history. Researchers involved in this work have described Webb as poised to drive a whole series of expansions of what they call the cosmic frontier, pushing into previously unimaginable redshifts, edging closer to the era of the very first stars ever to ignite, a moment in cosmic history that, only a few years ago, most astronomers assumed would remain permanently beyond direct observation. That pace of discovery is also why MOEMZ14's specific composition matters so much to the researchers currently studying it. Unlike some of the stranger, more ambiguous objects Webb has turned up in its broader surveys of the early universe, MOEMZ14 appears to be composed almost entirely of light elements, hydrogen and helium, the two elements that existed in abundance immediately after the Big Bang, before generations of dying stars had the chance to forge anything heavier. Researchers studying it have noted that galaxies made up of nothing but these primordial elements, essentially untouched by any previous generation of stellar chemistry, are still, in a broader sense, waiting to be conclusively identified and confirmed. MOEMZ14 may represent one of our closest looks yet at exactly that kind of genuinely primordial structure. A galaxy assembled from material that has not yet been enriched by anything that came before it, because at this point in cosmic history, essentially nothing had come before it. Confirming that composition with real precision requires exactly the kind of detailed spectroscopic follow-up the MIT-led team performed, breaking the galaxy's light down wavelength by wavelength, rather than simply measuring its overall brightness, the same painstaking process that let them nail down its redshift in the first place. Sit with what that actually means for a moment. Every star in our own sun's own history, every planet, every atom of carbon or oxygen or iron that makes up the Earth and everything living on it, was forged inside earlier generations of stars, cooked in stellar furnaces, and then scattered back out into space when those stars eventually died. Material that had to be recycled at least once, sometimes many times over, before it could ever become part of a planet like ours. MOEMZ14 exists at a point in cosmic history before almost any of that recycling had happened yet. It is, in the most literal sense available to modern astronomy, about as close to the raw, unprocessed material of the early universe as anything humanity has ever directly observed and confirmed. None of this is settled science, and the astronomers most directly involved in this work have been consistent about saying so. A single galaxy, however extreme, however record-breaking, is one data point, and drawing sweeping conclusions about the failure of an entire cosmological model from one confirmed object would be exactly the kind of overreach responsible researchers are trying to avoid. What MOEMZ14 represents, more precisely, is one especially sharp piece of evidence inside a much larger ongoing investigation, evidence that keeps accumulating, discovery after discovery, pointing toward the same basic possibility, that the true story of how the first galaxies in the universe managed to form, grow, and shine this brightly, this early may be meaningfully different from the story astronomers had settled on before Webb ever had the chance to look this deep into cosmic history. Right now, MOEMZ14 sits at the very edge of what humanity has ever directly confirmed about the universe's own beginning, a single point of ancient light stretched and reddened by billions of years. of cosmic expansion, carrying information about a moment in time so early that almost nothing about how structure actually formed there has been fully worked out yet. And astronomers already fully expect this exact record to fall again, possibly within the very near future, as Webb and eventually the Nancy Grace Roman Space Telescope, currently scheduled to join it, continue combing through the deepest reaches of observable time in search of whatever came before it. It is worth pausing on how strange that expectation actually is, when you think about it directly. A discovery this significant, a genuine record for the most distant confirmed structure in the entire history of astronomy, is already being treated, by the very scientists who found it, as temporary, a placeholder that will almost certainly be replaced within a matter of months or years, not decades. That is not a criticism of the discovery. It is a reflection of how much observational capability has changed in an extremely short window of time. For the vast majority of the history of astronomy, records like this one stood for years, sometimes decades, simply because the instruments capable of pushing further did not yet exist. Webb has compressed that timeline dramatically, breaking its own distance record repeatedly within the span of a single year. Each new discovery arriving not as a final answer, but as a fresh data point in an investigation that is still very much unfolding in real time. The Nancy Grace Roman Space Telescope, expected to launch before the end of this year, will only accelerate that pace further, carrying a field of view roughly 100 times larger than Webb's, designed specifically to survey enormous swaths of sky quickly, flagging promising high redshift candidates for Webb itself to then follow up on with the same kind of detailed spectroscopic confirmation that nailed down MOEM-Z14's exact distance. That compression matters for another reason too. Every additional confirmed galaxy at these extreme redshifts adds another data point to the growing catalog of objects that appear brighter, more massive, or more developed than the standard model predicts they should be at this earliest stage in cosmic history. A single unusual galaxy could plausibly be dismissed as a statistical outlier, an unlikely but not impossible fluke sitting at the extreme edge of a normal distribution. A second one, confirmed within months, at an even earlier point in cosmic time, is much harder to wave away that easily. And if a third, a fourth, or a dozen more turn up in the coming years, each one following the same basic pattern, unusually bright, unusually early, unusually developed, the case that something in the standard model genuinely needs revision only grows stronger with every new confirmation. That is precisely the situation astronomers studying MOEM-Z14 currently find themselves in, watching a pattern accumulate in real time, one record-breaking discovery at a time, without yet having a fully settled explanation for why the pattern keeps repeating. None of this makes the standard model of cosmology wrong, and it would be a significant overstatement to suggest that it does. The same basic framework that struggles to explain how MOEM-Z14 formed this early has also successfully predicted an enormous range of other observations across decades of independent research, from the large-scale structure of the cosmic web to the precise ratios of light elements produced in the first few minutes after the Big Bang. What discoveries like MOEM-Z14 actually represent is a genuine, unresolved tension at one specific edge of that otherwise successful framework, the very earliest moments of galaxy formation. A regime that, until Webb existed, had never actually been directly tested by observation at all. Whether that tension eventually gets resolved by refining our understanding of how efficiently the earliest stars formed, by revising assumptions about the earliest black holes, or by something more fundamental about the behavior of dark matter itself, remains one of the most actively contested open questions in modern astrophysics. And MOEM-Z14, for however long it holds its current record, sits right at the center of that unresolved argument. If this is the kind of story you want more of, subscribe, and let me know in the comments how far back in time you think Webb will end up seeing before its mission is finally done.